So welcome back to another edition of Rust Munich Meetup. This is the 5th edition now. Corona keeps stretching on, so this is going to continue for the foreseeable future. Tonight we have two talks, one by Sven, who's going to take the stage first, and then followed by Andrew, about an entirely different topic, but you're going to see. And yeah, Sven, take it away.
All right. Thank you, Bernard. Then, welcome everyone to the Rust Munich Meetup number 5. And today's the talk is about secure computing, and it's being an interactive intro into building a unikernel, actually. So let's move on. So, quick intro of myself. So my name is Sven, and I'm the author of two Rust tools. One is Hexagonal RS, and the other is T-Rec, that is a terminal recorder. And I'm also the maintainer of Cargo Generate, a little tool that helps you getting projects up and running. So with boilerplate elimination. Also the co-host here of the Rust Munich Meetup meanwhile. And yeah, sometimes I write about Rust learning. So yeah, you can find me also on Twitter, on GitHub, and on DevTow, where I write a bit. And yeah, feel free to reach out if you have questions or, I don't know, comments. Feedback is always appreciated. So today, I want that you have those takeaways. So first of all, what is a unikernel? We should just briefly discuss that, so at least you know. Then what is Rusty Hermit? And the last thing, how to build your own application as a unikernel. That is the interactive part, basically. So we build together two, maybe even three.
Your screen is scrambled.
Damn it. Just a second.
Don't really know. Yeah,
is it half now?
Yeah, half.
Okay, damn it. Firefox. Yeah. Maybe if I stop screen sharing. Just 1 second. I will try. So should be back, better. But yeah, I guess it will happen again. Let's see. Yeah, I'm sorry about that. Didn't test it properly before with this Firefox. All right, so yeah, last thing, we will build 2 or 3 applications as a unikernel and launch it, and then have a short wrap up. So the first, I guess it's is the screen now again, the bottom part is not visible, right?
Yeah.
All right. All right, then I try to just explain what's on the bottom. I'm very sorry about that. So this is the little intro, why the hell all this. So unikernel, so yeah, why we should even talk about that. And here, this is just a little summary that just recently there was a discovering that even a bug in a Wi-Fi module in the Realtek chip allows an exploitation. So a lot of routers are like affected from it. And also we see that, memory safety basically is the root of all evil, basically causes all the bugs. And that whole like, that whole thinking about, what we can do about increasing memory safetiness brings us to like two topics. One is like eliminating the attack vector by as much removing layers as possible. And the other is, of course, Rust. That's a thing where Rust shines, right? So I guess we can bring those two things together. And so this is basically the idea. So let's see. Okay, yeah, you're missing something on the slide. So on the very bottom, you see the operating system layer with the Ethernet. So this is an illustration how a virtual machine like normally works. So you have on the very bottom, you have the operating system, then you have this hypervisor, and then on top you have the OS. Normally, like a full-blown Linux, or if you have something like Docker, then it's like, so to say, isolated kernel area. And then on top you have the application normally that serves, the purpose, right? So you have all these layers, and that is basically something that can be eliminated. So this is actually, as you see it here, we would replace the OS and the application by just an application. So it's one box, and the whole operating system comes, so to say, as a library that is linked together on your application. And that is, so to say, the idea of a unikernel. So you're not running a full-fledged kernel with, a lot of other processes and even other responsibilities. You just have your application, and the whole kernel is part of it. And that, of course, eliminates a lot of attack surface. So let's see. So here, so here we see the bullet points for it. So a unikernel basically has a single-purpose virtual machine. It's very, very lightweight. It's normally also very performant. To give an example, there's another unikernel called Jitsu that acts as a DNS server. And while your DNS request is being served, it will launch the application as a kernel in matter of like microseconds, and then basically can serve the request. They are also normally like more secure because, as I mentioned already, a lot of layers are gone. And the last point here is like this memory isolation between safe and unsafe kernel code is or has been shown to be possible with Rusty Hermit. So there's actually, behind this link, there's a paper that was published by one of the authors of Rusty Hermit, and they've shown a very neat trick on the Intel assembly like instruction set to use to have it isolated. So it's very cool stuff. So then let's talk about one specific example of the unikernel that we have a look today. That will be Rusty Hermit. So Rusty Hermit is basically the unikernel. It is written in Rust, obviously. It uses this small TCP as a safe network stack. That is just a regular crate that doesn't depend on any standard library. Then it uses also libhermit RS, which is this library, this OS as a library component. Then as far as Rust is concerned, it compiles down as an own architecture. So they call it like -hermit as an architecture. And there's also a bootloader for it that is Rusty Loader. We will have a look at this. That is needed for QEMU, for the EMU. And for all those people that doesn't want to use QEMU, there is an own hypervisor that they also provide. It's a very minimalistic hypervisor that can launch Hermit applications. So I guess that was the forward. Let's see if we can get hands-on code. And here's the link to the GitHub repo. And yeah, let's just try it out, I guess. So let me see if I can. I'm really tempted to download Chrome and switch, but I don't know how long this will take. So yeah, what you see here is the repo from Hermit core. So it's on GitHub, Hermit core, an own organization, and there you have all the repositories. So in this presentation today, I want to use QEMU, and for this we need the loader. So Rusty Loader is the repo, and to explain it briefly, so maybe we can just start by cloning it. Yeah, so so as you see, they need nightly, and they provide a Rust tool chain.
Do you want to quickly switch to Chrome?
Yeah,
just
probably.
Asking.
Yeah.
And if you press the link, then it should be, yeah, 5 seconds.
Yeah. The issue is need to quickly install it.
Oh, I see.
I'm sorry. Yeah, I just dismissed the Google stuff a couple of weeks ago. So
please hold the line.
Okay, I guess I need also to give the permissions to the app, which takes also a second. So I will be back, in a minute or so. All right, see you.
So yeah, this is time for a short pee break or grabbing another beer or whatever your beverage of choice is. We'll be right back. No, that's a lot better.
Yeah, seems to work. Cool. All right. Again, very sorry about that. So let's move on. We have like cloned the Rusty Loader project from Hermit Core, and I want to point out that here we have the Rust toolchain file that sets everything to nightly, and as a prerequisite, we also need to install QEMU and ASM, which is, I did it already, so it's just for completeness. You find also all these installation notes on the repo that you find here. My account and then Rust Munich Meetup 5. And there we have here the setup for Mac and the setup for Linux, basically. All right, so having that done, we need to build it. And that's pretty simple. So they come with a little make file. So we have just to set release to 1 and then run make. And then basically everything should go quite smooth. So here you see also the components that I use. So it's Rust source and LLVM tools. But yeah, as said, they are all defined in the Rust toolchain, so you don't have to install them yourself and even not need to defaultly switch to nightly. So I guess we're getting close. So now in target, we should see the loader. And interestingly enough, there's in the makefile, there's a little magic that converts it to a 32-bit binary. And here's the code. So if you want to have a look how they do it, it's all here. All right, so having this step done gives us the bootloader. This is just one component. So let's now start with a little demo project. And for this, I have a little template prepared that you could use. And we say just hello hermit, just a simply hello world. And we are using QEMU, and for now, we're using this network chip here. I will talk about the network chips in a bit, so don't worry. So we have now the Hello Hermit. It's a simple Rust project, so there's nothing special on it. So again, we have a Rust toolchain here that points us to Nightly, and we have also a little cargo config. This cargo config allows us basically to run the application as a regular application. So like cargo run would basically launch QEMU and would configure everything as we would need it. So one assumption that is baked into this template is that in ... from here on, we find the Rusty loader and target and so on. And yeah, this is like needed as the kernel in the QEMU sense, and our application will be provided as a init.rd, so in drum disk. Okay, so let's have a look. Okay, sorry, the code. Of course, that is also interesting. I mean, it's actually not so interesting. We have a little TCP listener here that binds to 000 and port 8080. And when a connection is accepted, it prints out a message with the address of the remote, and it copies the data that comes in over. So it's basically a simple echo TCP server. So let's have a look. Cargo build minus release should look very similar. While it compiles, we can have a look at the cargo toml. So I would say screw that for now. This is experimental. But here is the interesting piece. So the target OS, as I mentioned before, it compiles down to an own architecture. So it has also an own OS that is Hermit. And for this target architecture, there are dependencies defined, and this is like Hermit sys in a version 01 star, and some features are provided. This is the small TCP stack, and additionally, we have a DHCP server that is also compiled in as a feature. And yeah, some optimization stuff, but this is not very important. So then that was that shouldn't be the case. Let's retry here, because this build dependency was still here in the cargo toml that might have caused that.
Could you increase the font size a bit in VS Code?
Sure.
Perfect. Thank you.
Okay, so yeah, this was really because of the experimental stuff that I had in the cargo toml left. So I will remove this in the final version. So let's see what we got here. Let's have a look at target, and there we see this specific architecture and release, and we have the Hello Hermit there. So could have a look what it is. So it's a regular ELF binary even dynamically linked. So let's do a cargo run. All right. You see basically a lot of output that is here the QEMU runs with the device, the network device configured. And the important thing is it does here a port 8080 host forwarding. So it's like a regular port forwarding from the inside to the outside, as you may notice all from Docker and so on. Then you get a bit of debug output from the loader, and then the kernel comes into the game. And yeah, it boots up, set up the heap, and a bit more. Here we got the Ethernet controller, the Realtek. And yeah, in the end, this then here is basically coming from our application that is fired up. So let's see how that would work. So we do a little netcat, localhost 8080, and we say, yeah, echo world, and we get echo world back. So this is like the first example. And on the left side, you see the debug output basically from the incoming connection here, which we had in our main file, just to show it again. So TCP listener binds, then when it accepts an incoming connection, prints out this incoming connection from address, and this is what you can see here. And yeah, so all good. Let's see. There is also a different example, which is a little HTTP server. I guess this would be the next thing that might be interesting. So I will not like start this from scratch because I have like pre-prepared that, and yeah, as said, you can find this all in the repo. So let me just copy that stuff over. It's HTTP hermit to here. So let's have a look. So HTTP hermit is basically a tiny HTTP server. So it depends on tiny HTTP in a little modified version. So we need to copy that also over. Okay, so what is the difference? I believe this was all related to default feature enablement that is normally on the tiny HTTP, which is a regular crate that you can find on crates.io. Has some more things enabled, and the Hermit guys, they disabled a couple of things here to get it running. Okay, then let's have a look. Here the same procedure basically. we missing? Okay, should be. Tiny vec macros. Where are they from? Okay, that is interesting. Yeah, obviously the standard crate should not be there. So let's see. Yeah, well, okay. I have no explanation why that behaves now this way. Should not be. Can I have a little check? How it was here. I mean, what's the difference? Maybe I missed something. No. All right. Yeah, I'm sorry about that. No explanation here why that's the case. Yeah. Let's see. So yeah, let's quickly wrap up. So we have now like skipped the simple hello world application. It just echoes hello world. We directly jump to the HTTP echo server. And yeah, this was like the official demonstration that I wanted to give. Then there's a little bonus thing if you ask yourself, so how is this now like usable? There's also like a nice wiki page about how to run this on a Kubernetes system. It's not like a regular Kubernetes one. It's like KubeVirt that uses QEMU as a launcher for the virtualization, basically. So yeah, you can read this on the wiki page. It's also really interesting, and yeah, find a couple of more links and references in the repo. And let's have a look at the final slides. So to sum up the caveats that we have, oh, sorry. Yeah, so basically it's a single process since everything is like one kernel that runs and there's no such thing as like threading or anything that would require a fork. So we don't have a Linux kernel at all. This is just this unikernel. This is a very minimalistic fabric on the bare metal. So we don't have fork. And right now there's also no non-blocking IO. I had a quick chat with the authors behind Rusty Hermit, and they're currently working on making non-blocking IO, so meaning async and await, essentially available. Until then, it is not there. and the network drivers are also quite limited. So we have two things only available, which is Word.io. That is a feature that you can try out under Linux and works quite well. It virtualizes basically the existing Ethernet. I mean, it not like creates a dedicated layer for it, but it shares somehow the hardware and exposes portion of the hardware to the guests. So this allows quite fast network stuff, whereas the RTL 8139 chip is, as far as I've understood, it is an own virtual network adapter that is provided by QEMU, so which is software emulation. So it's quite a slow thing. So we could have a little like look at this, how slow that is, if you want to know it. I was quite curious about how does this, I mean, how bad it is or not. And which is now not the HTTP. Yeah, so not really. Yeah, so I cannot show it now because we didn't got the HTTP server running. However, so parallel requests would of course not work because we don't have fork and we don't have async. And single requests, they would respond in the range of 1 second, roughly. So being this virtual setup on localhost, everything, yeah, 1 second is quite slow. So yeah, that is not the best thing, I would say. So yeah, I don't know. I mean, I have also a Linux box and I've tested the Virtual.io there. So basically you create a tab device, and with this tab device, you can then like tunnel the traffic, and it worked faster, but I could not really say how much faster. And the last one, it's just a minor one. So it only works with Rust nightly. I guess, yeah, it is okay. I mean, if you look at other frameworks like Rocket, I believe, was also long time only possible with nightly. So I guess it's not really a problem since nightly is quite stable. Okay, so then here you got all the references and also this link with the paper that is really interesting to check out. And yeah, now, I mean, also later, you have the chance in the Discord to ask questions and answers. And thank you for listening. And yeah, sorry about the starting issues. And yeah, enjoy the other talks. Thank you.
Cool. Thank you very much. There is one question which is around real-time operating systems and if the Rusty Hermit also supports no STD. I guess the answer to no STD is kind of yes. If you can support STD, you can also support no STD. But I guess you would have to bring your own x86 kind of replacement for Rusty Hermit then.
Yeah, so yeah, from what I've understood is that Rusty Hermit, since it is like the kernel library, basically provides you with all the STD features, essentially. So your application code could still depend on STD. This is no problem because it gets substituted by the Rusty Hermit architecture, basically. So and Rusty Hermit, like the kernel OS itself, does not depend on any other thing. I mean, even this TCP, small TCP, doesn't depend on STD. It is designed to be really for bare metal. So yeah, there's no support for STD needed. If that answers the question.
Let's see.
Let's see here. All right. I mean, we could also after the other talks, you can have a little chat. ARM, yeah, okay. The question is if it also could support other architectures, and the answer is yes, but I have not tried it. So the guys have implemented ARM 64 support, so it compiles then down not to x86, but then to ARM. And yeah, I guess it should work the same way, but yeah, according to the docs, I didn't found so much. So maybe that all is not so stable. Yeah, so let's see. I guess it's a pretty young project, and they have still some homework to do, specifically async and await, or without async and await, and just single threaded. That doesn't make so much sense in a productive scenario. Even if you use a Kubernetes system that would spin up QEMU emulators, that is way too costly compared to kernel level virtualization that is with Docker basically established. So, but once they got to async and await, I guess that is really, really rocking, because all the boilerplate basically is gone. It's all Rust, and it's going to be really rocking. So I'm looking forward to that. All right. Yeah, I guess. Thank you all. And handing over now to Bernard.
Cool. Thank you again. Thank you very much for your talk, giving some more insight on how to do virtualization with Rust, or get your application virtualized with Rust without an OS, and without the overhead of a fully fledged Docker container. Yeah. Our next guest speaker today is Andrew. Andrew's going to talk about his experiences in the medical AI industry. And yeah, Andrew, take it away.
Hi, warm greetings to everyone. Let me try and share my screen. Let me know if that's okay.
Looks good.
Awesome. So hi, yeah, thanks for letting me talk. So Rust in the medical sector, probably not the most exciting title, but that's the challenge. Basically, I'm an engineer, just a software engineer working for a company called Deepsea in Ostbahnhof. And we're trying to bring AI to radiologists. And what I thought I'd do with this talk is just share some of my experiences transitioning to Rust within that organization, some of the challenges that we have, some of the positives that we found. And yeah, that's the aim of this talk. So I'm a journeyman. I've been doing Rust for about coming up to 6 months now. So I thought that's a perfect opportunity to share my perspective with the community. And hopefully some other people might be inspired, if they're at a journeyman level, to also make some progress with Rust. So what is Deepsea? What's the challenge? Don't want to talk too much about the company, but set the stage. So essentially this is like a radiologist working in the hospital, and essentially what we're trying to do is add like a spell checker to the experience of diagnosing health issues. So we have an AI expertise that we offer in terms of being able to build models that detect anomalies in scans. And part of that journey was basically to convince hospitals and other practices that take advantage of some of the progress that's being made in the AI community to help radiologists. So we want to basically make radiologists as productive as possible, taking advantage of new technologies like AI. So this is kind of like the elevator pitch. Essentially, there's a skills gap. There are a lot more patients taking advantage of med tech, but there are a lot less professionals coming out of university to actually take on that load. So we see an opportunity with AI to provide an assistance, perhaps to junior radiologists, or to kind of perform a level of screening, or to push the skills to the edge where experts might not physically be able to be. and essentially assist the radiologists. So it's quite an intensive experience for radiologists trying to concentrate and find anomalies in X-rays or in either scans. So the AI really kind of provides, a comfort in terms of any misdiagnosis. And it turns out that because these radiologists are under pressure, there are a noticeable ratio of false diagnosis. So what the AI provides is an opportunity to bring that percentage down. And so, yeah, that's what we're basically trying to achieve. So like a high level of our solution, we basically provide like a edge computing capability to hospitals and radiology and practices, where we want to basically have AI running in the cloud. We want to securely connect to some patient information data and medical imagery devices, and essentially route scans to our cloud, perform inferencing, and then send the results back down to the on-premise installations. And yeah, we try and basically build, once we made progress, getting a presence inside the IT organization, and we noticed that some of the customers were actually quite interested in helping, in us helping them get other AI models into their IT infrastructure. So what we're interested in also is providing like a marketplace for not only our own AI capabilities, but other third parties might want to join the party. So this is like just a little overview of the stack, how it evolved. We had like initial MVP. There was some Python expertise and some JavaScript expertise. So kind of start off as you probably would with a Node.js backend and some JavaScript on the front end, React, and some PyTorch, essentially to perform the inferencing. We had a second MVP where we brought in Go to kind of get, let's say, without burning any bridges, a more mature backend. And obviously lift and shift everything onto Kubernetes, get monitoring in place, and address some of the scalability issues that we wanted to, or scalability targets that we want to reach for our product. And recently, we've basically switched out the Golang backend to Rust. And anyone who's interested on the kind of DevOps side, we've kind of moved the abstraction layer higher up to Knative. We have a bit of Kafka, we have a bit of Kubeflow, but this talk is about Rust. So why Rust? What were kind of the decision-making factors that we undertook to transition to Rust? If you're already using Rust in your company or in production, then you probably know some of these things. If you're evaluating, this slide is for you. So some of the things that we found very attractive from Rust, moving from Golang, was predictable under load. So as we started to get more and more images coming in, we wanted to basically have more confidence in production that the resource utilization that we were using was the best it could be, and especially if we're deploying to the edge where customers might have restricted IT resources or reduced IT resources, and being as efficient as possible with the resources that we have was important. Type-driven development. There's test-driven development, there's behavior-driven development. I like to call using Rust, well, it feels like type-driven development. So what I mean by that is, if you care about correctness, one of the questions we asked ourselves was, to what degree do we care about correctness of the system? And definitely Rust, at least what we're hearing from the community, with the type system, gave us the ability to have more confidence about whether our application was correct. Efficient deployment model. Yeah, we just saw an awesome demo about unikernels. We all know, or at least if you haven't found out yet, Rust is efficient, it's fast, and that's very important also on the edge, because we want to be taking advantage of limited bandwidth to download new versions of our software or use up the least amount of disk space, for example, which I have a slide on. The medical industry is a C++ ecosystem, so there's a couple of times where you need to dip your toe into C++ and do some integration, and having the first-class support for ABI and foreign interfaces just really made it feel comfortable. Integrating with some third-party plugins or other libraries in the medical sector. And first-class WebAssembly support, something I'll be talking about later. So I have a couple of graphs, I apologize. So this is kind of like, we were trying to drive efficiency to be the best it can as possible. And some of the containers that we are using in our system, we observed over time, we saw, this was causing some problems. So for example, when we talk about cold starts, when people use the application, or when we're providing updates to the edge devices, we want to keep the container sizes down as much as possible. So this graph, you can probably imagine which of the containers are built in Rust and which of the containers are built in other languages. So there's a couple of outliers here because we have some AI models, but if I take out the outliers, then still you get a feeling for the disparity in container sizes that we're working with when we move to Rust. And moving from our previous MVP, our second MVP, which is written in Golang, which is kind of a monolith application, you can see the breakdown by language. And it just happens that actually all of the Rust services combined are still less than the monolithic Golang application that we built for the second MVP. When we look at resource utilization, we're running our application on Kubernetes, as I said, and we're using Knative, which is basically like a opinionated microservices stack for Kubernetes applications. And here we can see the green line is basically the Kubernetes infrastructure, basically proxying requests to our microservices. And the golden line is basically our application. And so now we've actually got to the point where our application is using less resources than the infrastructure that runs our application. So that in itself, I think just tells you where we are now, and it's a good place to be, feels good. I'm not quite sure if I want to give this feedback back to the Knative community, but it's nice to see that we use as little resources as possible and respect the resources that we're given. Second point, type-driven development. So I don't know if anyone's heard of event storming, but it's essentially a practice where multiple teams get together and agree the domain language and the types and the interfaces between different services, how the whole system should behave as a whole. So we have a similar practice. We get together in our team and we agree, how, from an architecture point of view, how the system should actually work, and then the teams go away and actually implement those interfaces, and we come together, integrate, and hopefully the system works. So interesting learning from this experience was, what did Rust teach us when we went through this event storming process? So we have this process we call Octopus, because we're a company, we're called Deepsea. I guess we have some association with ocean animals. And this is an example of some of the output of some of the discussions, right? So basically this is a JSON file or JSON schema which describes some of the events in our event-driven architecture that float around the system. And essentially what happens is we have like a merge request process where we can kind of capture like a architecture decision record where someone would essentially make a proposal to add some new events or some changes to the system. Then people in different teams would generate the code based upon those types, and essentially we would implement the changes in our respective systems. One of the great learnings about this experience was that although we had proposals that seemed valid on the surface, the Rust compiler saved us. The Rust compiler essentially said, there's a couple of edge cases, right? So in many languages, the optional type isn't really respected in another language, right? There are null pointers possible. So in other languages, for example, Go or in Python, you wouldn't really know if there was an issue, whether something was empty or not, until you actually run the application. So in this process, it was quite interesting. Observation was that we could just ask the Rust compiler to compile the proposal. And in many cases, it did actually identify some edge cases where essentially in the merge request, we had to make iterations to correct some of the types that were defined as a result of the feedback from the Rust compiler. So that was a situation where I'd say, people talk about the borrow checker. I'm very happy with the Rust compiler. It corrects me. I learned something from the Rust compiler. Okay. My business, the way I thought the system should work, there's an edge case. So that was a big plus. First-class WebAssembly support. So what does that really mean in the context of the medical industry? So I'm sure many of you are aware that WebAssembly is trending, and in Rust you can build front-end applications. You can build front-end browser-based applications in Rust. There's also other trends on the WASM side, right? We have things like WASI. People are starting to run WASM workloads on the server side, looking to replace containers, perhaps the at least traditional form of containers with Docker or Containerd and Kubernetes. There are a number of advantages there in terms of getting better efficiency, reaching different compile targets. The list goes on. But another interesting thing is a lot of community projects where previously extensions were written in Lua script, now they support running WebAssembly workloads. So that technically means that you can contribute to a project that has a scripting extensibility endpoint and don't have to write Lua script. You can just write Rust, compile to WASM, and have it run as an extension to that project. So on the front end side, this is what we've been evaluating. This is what your front end and back end project looks like when you're writing WebAssembly with Vue. So just have another workspace. It's called front end. It's Rust. You have another workspace back end. It's Rust. And yeah, you go and tell that to your Node.js colleagues. You say, hey, I'm also using the same language on the front end and back end. And I suppose coming back to the other points, if you care about correctness, the question is, how much do you care about the correctness of your front end? So this is an opportunity, definitely suggest someone check out the Vue framework. Very satisfied with that, and have some points I'll talk about later about how we plan to use that at Deepsea. So essentially, our application on the right-hand side is where the radiologist spends most of their time. But we found that as minimal as this looks, there's a lot of complexity going on, and more complexity that occurs between change events. The more you have to calculate when you redraw the world. So slowly we're reaching points where, we're having performance issues on the front end in Vue.js, where redrawing the world 60 frames a second, might be an issue, especially as we start to jump into new use cases. So the selling point, at least for Rust in that area, would be Rust is faster than JavaScript. Or, when we want to recalculate the world, we could do it in Rust. Let's see, is there a benefit there in terms of performance? And especially when you start to move into different UI techniques like drawing to the canvas and doing blit bits and calculating viewports and matrix transformations, then moving to something like WebAssembly, moving to something like Rust is very compelling. So that's something we're evaluating after we made some progress with just initial prototypes. So these are just some learnings that I wanted to present back from my experience. So I've been learning Rust for coming up to 6 months now. And the observations that I made within this project would be, there's a learning curve. I think we all know about it. Maybe we can just be honest about it. My suggestion, my estimate is a 1 month active learning curve. Someone who doesn't know anything about Rust. That was different maybe for Golang, probably about a week, maybe 2 weeks. But 1 month for Rust. If you're coming from another language where you have a daily or every minute relationship with some kind of code coverage tool, you're going to probably be disappointed in Rust. I mean, maybe someone can give me a tip afterwards what tools they're using. We're using tarpaulin. Works really well, but in terms of editor integration and quick feedback, yeah, there's some trade-offs with Rust. Yes, we're really impressed with the security ecosystem. That it definitely helps us when we're looking to convince some of our customers that we take security seriously. And yeah, the cargo audit feature has been really nice, and just having that run in the CI/CD pipelines. Yeah, unit test feedback. I mean, you save a file, you try and run a cargo test. There's a lag, especially if you're coming from a different language. So, but it's a trade-off that I'm accepting at the moment. And yeah, I mean, probably some stuff we already know. Community is diverse, which is great. But sometimes you want to have like an opinionated presentation or workflow about how you should, which web framework should you typically do for a microservice, or is it Tokyo or is it async stood? But yeah, I think there's still progress to be made, so it's nothing that's really kind of stopping us from being productive. We're just observing, where these framework wars are going and trying to, catch up. And if you're coming from another language, yeah, implement trait for an external type. It's part of the learning curve, especially if you're trying to do, which I would say is called idiomatic hexagonal architecture. What does that mean? So if you're coming from maybe another tool chain, maybe another language, you might be getting engraved in your head at some point to think about your application in a hexagonal form, which basically means that we try and define our entities and our use cases in the core. And then as we go out of the layer, we make conscious decisions about where we want to define interfaces and which modules should basically have dependencies in which direction. And if you're not careful, you could get into a situation where, depending whether some of these modules are in the same crate or outside of the core, maybe within a workspace, then you get some issues. And I think it's probably just a case of finding out what the idiomatic way is in Rust to do hexagonal architecture. But in our case, it's not a showstopper. We're basically trying to reduce the complexity in all of our services such that we don't have to think too much about hexagonal architecture. And yeah, if anyone uses Vim Startify, yeah, maybe we need to rethink the solution to the problem. And we need code generators. So some stuff we have on the roadmap ahead, like we see a strategic interest to rewrite our front end WebAssembly, and looking at the choice of languages that are available there and approaches, Rust looks like a very strong candidate. We plan also to go into the medical industry, where we have traditionally a C++ presence, and make contributions to transition as much as possible to Rust. We're definitely excited about WASI, Crustlet, and other runtimes to run our Rust workloads more efficient. But I definitely was blown away by the unikernel presentation, so that's definitely something to look at the trade-offs. Yeah, and we're also working on an operating system, kind of like a distro, which includes a whole bunch of components for a medical AI edge presence. And previously, some of those components might have been written in Golang, but now in Rust, definitely seems like a more efficient toolchain to use when building an operating system. So thank you. I hope that was useful. I hope that was confidence inspiring for any of you that are thinking about persuading your boss to use Rust. It's been a great success for us, and I can jump into more detail about any of those particular areas, but I wanted to respect the time. So if you have any questions, please let me know.
Thank you very much. That was very insightful. I find it interesting that you kind of that in your experience that 1 month full-time learning Rust would be enough. Like my learning experience was kind of different. I think until I understood like concepts like late bound lifetimes, it was probably more like a year.
Yes. So, I mean, we can talk about different levels of proficiency, right? So, if you're in a place where you're looking to just build an application, maybe a business application, right? There's kind of a golden path where I think you can navigate away from certain sections of Rust, and you can still draw confidence. So, you might spend most of your time not writing any C++ integration, not working with lifetimes. You may not even have to write an async trait, and that's like the sweet spot that you might want to stay in. And there are other areas which are more exciting and glamorous, and I would definitely say that requires more than 1 month, right? But in terms of just drawing confidence and being able to be successful in whatever industry you are, I think, 1 month actively is more than enough time.
Cool.
Sure.
There's one question right now. What Rust backend service is in use? Are you using a more low-level approach, like based on Hyper, or more higher level, like Rocket?
So we basically are very heavy on GraphQL and cloud events. So a lot of the community support for those, they're more high-level packages like Warp or Actix. So that's basically the level we are at the moment. And it feels quite comfortable. There are no things missing in there, especially coming from other languages like Golang and Node. There was more than enough crates in the ecosystem for us to be productive.
Yeah, that's for sure like a huge palette to choose from.
Absolutely. I think it's really a surprise to any newcomer coming to Rust, because you might think that the crate ecosystem is limited, but it's a pleasant surprise how many great crates there are out there.
It was a different story 4 years ago.
It's like it turned up at the right time.
Yeah.
Sure.
All right. If there are any further questions, then I guess we're gonna continue in Discord. Again, thank you very much, and yeah, would be glad to have you back here at some point in the future. All right. This was the 5th edition. The next one will contain another set of cool talks, obviously, as always. Yeah, thank you for tuning in. I'd be happy to have a chat with you on Discord right now. Thank you very much, and see you next time.